In the last class we discussed about the Mosfet device as an amplifier, and in continuation with the earlier discussion, today we will be going into details of amplification. In relation with the Mosfet device, we have got one important parameter, which is the transconductance of the Mosfet. Now, the transconductance, which is symbolically denoted by small g, small m, this is given by the ratio between the small drain current, that means the small signal or AC drain current, and the gate to source AC voltage. So, now if we look into the transfer characteristic of the Mosfet device, from the transfer characteristic we can find out the transconductance. So, now how to do that? Let us recall the transfer characteristic of the Mosfet device. So, the drain current versus the gate to source curve, which is the transfer characteristic, starting from the threshold voltage, and we should know actually more than one point to draw the transfer characteristic. So, from the current equation ID equal to K into VGS minus VT whole square, we can find out some points and join these points to get the transfer characteristic curve. Now, let Q be the operating point, which is fixed by the DC biasing circuit. Now, how the biasing is done in Mosfet amplifier, that we have yet to discuss, and we are going to do that soon. So, the Q point, let us assume that it is located here, and the coordinates of the Q point are given by capital VGS and capital ID. Now, if we now find out the slope of this transfer characteristic at the point Q, that will be giving us the transconductance GM. How to find out that slope? Around the operating point, we take a small region where the characteristic can be assumed to be linear, because only within a small region around the operating point we can assume that the portion is linear, because it is a piecewise linear characteristic if we take, in order just to find out the slope. So, the slope of this transfer characteristic at the Q point, if we find out, which is given by the small difference in this current in the drain divided by the difference in this voltage, which is nothing but the small ID by small VGS, that will give the transconductance. So, the small signal drain current, if we are denoting it by small I small d, it is a, for example, we are taking a triangular waveform, say triangular AC signal, which is a small I small d, means the signal, and corresponding gate to source voltage is a small VGS. So, corresponding points on the gate to source voltage axis drawn or projected from this current signal are these points, which will be giving us the voltage between gate to source. So, the slope is denoting the transconductance. Now, when we are using the Mosfet amplifier to amplify a small signal, then obviously we must know the voltage gain. Voltage gain means the ratio between the output voltage and input voltage. So, as we earlier in discussion of BJT as an amplifier, we have found out what is the voltage gain, current gain, etc. So, let us also proceed to find out the voltage gain for the Mosfet, and we are taking this small simple circuit as an example. What will be the voltage gain when we are giving an input small VGS? This is input, it is given at the gate to source terminal. This is the drain terminal, this is the gate terminal, source is grounded. This capital VGS or capital VDD are there which are required for biasing, because we know it is enhancement type N channel Mosfet. Gate to source voltage must be kept at positive and drain to source voltage must be kept at also positive. So, to achieve that, we need to have the DC biases which are VGS and VDD capital. Now, let us find out the voltage gain of the Mosfet amplifier. Because we are discussing the amplification, the gain of the amplifier is the ratio between the output voltage and the input voltage. Now, the output voltage at the drain is small v small d, and the input voltage which is applied between the gate and source is small VGS. So, this ratio will be giving you the voltage gain of the amplifier. So, now let us find out the voltage at this drain end. Now, when we will be writing the voltage equation, we will be writing the instantaneous voltage equation, that is small v capital D, because we are having, apart from the AC signal, we are having the DC signal, DC voltages also, which are required for biasing the Mosfet properly, because we know that it is an N channel enhancement type Mosfet device. We need to keep the gate to source voltage at a positive value and drain to source voltage should be also positive. So, to achieve that, we are having the two DC voltages as shown here, which are VGS, capital VGS and capital VDD. These two voltages are there to make the gate to source voltage positive. That means, gate is kept at a voltage positive with respect to the source. Similarly, the drain is kept at a voltage positive with respect to the source. These two conditions must be met in order to make the Mosfet on or make it conduct. Apart from these DC biasing voltages, of course, we have this signal small v small gs, which we need to amplify. So, now in order to write the voltage equation at the drain, if we want to write the voltage equation, in this situation we must write the instantaneous voltage equation. We are not considering DC and AC separately right now. We are going to write the instantaneous voltage equation. So, that equation will be what? Small v capital D equal to capital V d d minus small I capital D R d. So, this is the voltage equation. Now, that can be further written down by noting the fact that small I capital D is equal to capital I capital D plus small I small d. So, replacing this instantaneous current small I capital D by capital I d plus small I d, we are rewriting the equation which will be giving us the instantaneous voltage V d equal to V d d minus I d R d minus small I d R d. Now, we note this term V d d minus capital I d R d. This term is nothing but capital V capital D, because if we consider the DC quantity only, the drop V d d minus capital I d into R d will be giving you the DC drop. So, that is denoted by capital V capital D minus small I d R d. So, now if we again look into this equation, this is small I d, this is small I. So, now if we now consider this whole equation, which part will be only AC part? This part small I d into R d with a minus sign, this is the AC part, but other part is the DC part. So, now if we are concerned about the AC part only, because we are discussing an amplifier is amplifying a weak signal which is a AC signal. So, at the output also we will be concerned about the amplified AC signal. So, writing down the AC component or signal component of the drain voltage, which is nothing but small I small d into R d with a minus sign, and again this small I small d can be written as Gm into small Vgs, because we know what is Gm, Id small id by small Vgs. So, writing in that way, replacing the small id by small Gm into Vgs into this Rd is already there, we can now find out the ratio between the output voltage and the input voltage, output voltage being small v small d and input voltage being small v small gs. So, that is equal to what? If you take the ratio between Vd and Vgs, we have minus Gm Rd. So, this is the voltage gain of the Mosfet amplifier. Now, if we look into the term, we get that the Gm, the transconductance for the Mosfet, will be a parameter which is defined for a particular Mosfet. So, the transconductance multiplied by the resistance in the drain with a minus sign. So, voltage gain will be minus sign, means immediately we know that output voltage and input voltage have 180 degree out of phase. So, the phase difference of the output voltage from the input voltage is 180 degree. That is why this minus sign is coming into the term. So, now if we look into the output voltage and input voltage, let us apply a triangular voltage. We are just taking the example of a triangular voltage. It may be a sinusoidal voltage also. Just for easy drawing, we are taking a triangular voltage, nothing else than that. So, we are taking a triangular AC voltage which is VGS. So, this constant voltage capital V capital GS is the DC biasing voltage between gate to source. This will be present. On it is superimposed a small v small gs, and the instantaneous value of the voltage between gate to source is VGS capital plus small VGS. So, at any instant if we want to find out what is the instantaneous voltage, means at any instant the voltage between gate to source will be found out by adding these two, capital VGS and small VGS. So, starting from this DC value, it is rising because we are applying a sinusoidal voltage, not sinusoidal, triangular voltage. It will be rising in this fashion of a triangular wave, rising and then falling. So, this will be the profile of the instantaneous voltage between gate to source. Corresponding to that input voltage, what will be the voltage at the drain end? The instantaneous voltage at the drain, which is small v capital D. As shown here, it is 180 degree out of phase. When the peak of the gate to source voltage is appearing, corresponding drain voltage will be having the negative peak. So, this point corresponds to the negative peak, and the negative peak of the input voltage will be corresponding to the positive peak of the drain voltage. So, we will be getting the output voltage at the drain as shown here. It is amplified no doubt, but out of phase by 180 degree. Now, in the absence of the signal for the DC VGS, we are having the DC VD. So, this is the constant part is the DC value of the drain voltage, and on it is superimposed the AC portion or small v small d. This is actually small v small d, which is superimposed on the capital V capital D. So, the output voltage and input voltage waveforms, as we see here, they are just having 180 degree out of phase. So, now the amplifier as such is amplifying an AC signal, and it is having a voltage gain given by minus Gm into Rd, Rd being the resistance at the drain, and the minus sign is signifying the phase reversal. Now, as I have mentioned earlier, the amplifier is having a DC biasing circuit. So, in order to analyze the amplifier using the small signal model, we must first of all set the operating point properly. Now, the biasing methods which are used for setting the operating point properly will be now discussed. Now, the operating point, as you know, is the DC point which gives you the value of the DC voltage and the DC current when no signal is applied. Unless we fix the operating point at a proper location in the transfer characteristic, our amplification may suffer, because we know that the Mosfet device is under saturation when it is used as an amplifier. So, throughout its operation, the condition for saturation should be maintained, and in order to maintain the condition for saturation, at any point throughout its operation, the drain to source voltage must be greater than the difference between the gate to source voltage and the threshold voltage. So, VGS minus VT, that should be smaller than VDS. Now, we can see that in order to satisfy this condition, your operating point must be located properly, because if it is not located properly, either towards the if it is towards the upper end or towards the lower end, that means it is, if it is too near the cutoff like this, if it is transfer characteristic is say like this, and we are having an operating point which is not properly selected like the middle way, it is say here or above, then what will happen? It will be difficult to maintain this condition. So, we must first of all fix the operating point properly, and for that we must bias the circuit properly, because if it is not located properly, what will happen that at any point when the signal is applied, the gate to source voltage may not be sufficient to make this whole quantity less than the drain to source voltage. So, we will be now discussing about the DC biasing schemes which is required for proper selection of the operating point. First method that we are going to discuss is the feedback biasing method. It is similar to the methods of biasing which were used in BJT. So, if we have understood the biasing in BJT, then it will not be difficult to understand, because it is in the similar way. Even without discussing much, we can understand the biasing methods. So, for example, we will be taking these two biasing methods, one is the feedback biasing method and the other is the voltage divider biasing methods as applied to the n channel enhancement type Mosfet device. So, this circuit here is employing this n channel Mosfet enhancement type Mosfet, as is clear from the symbol. This is the amplifier circuit. It is having the DC biasing as well as it is employing a small signal which is to be amplified. So, feedback biasing means at a drain end we are having a resistance RG to the gate. Now, there are capacitances. The reason for applying these capacitances are that we want to block the DC from the AC, because we want to get the amplified AC output and we do not want it to be corrupted by the DC signal. That is why there are coupling capacitors. The purpose of using the coupling capacitors are to block the DC. Now, in this circuit, as we have seen, the drain and gate is having a resistance RG in between them. This is comparatively high resistance RG which is connected. The output is obtained at this N and this voltage is known as VD, that is the drain voltage, which is the output voltage which should be amplified and not having any change in the shape as regards the input voltage. Input and output voltage must be similar in shape, although there may be phase reversal, but there should not be any distortion. So, we need to apply the input signal small enough to guarantee that distortionless amplification. Now, if we are now having this circuit, what will be happening if we look into the gate terminal? The gate current is 0, because we know that Ig is 0 for a MOSFET. There cannot be any gate current. The gate and the body of the MOSFET or the substrate is having a silicon dioxide in between, which is an insulating layer. So, the gate current cannot flow, it is 0. So, if the gate current is 0, obviously this voltage across this resistance is 0. So, if this voltage is 0, that means the drain and the gate point is just like short circuited. So, we will use that it is like a short circuited path between the drain and the source. Since Ig is equal to 0, for a MOSFET device we know that Ig or gate current is 0. So, this short circuited path exists between drain and the source. So, if we now draw the DC equivalent circuit, forgetting about the AC input, we are having this circuit which is having the resistance RD at the drain and gate being short circuited. This circuit is bereft of the capacitors, it is not having the capacitors, since this is equivalent circuit, it is open circuit for DC, the capacitor is making it open circuit for DC. So, the capacitors can simply be removed in the DC equivalent circuit, and the simplified DC equivalent circuit appears as like as it is shown in figure. So, now what will be the drain voltage with respect to source? VDS equal to VGS, because we know that this point and this point are same, there is no difference as there is no drop, it is a short circuited path. So, VD is equal to VS, VD equal to VG, or VDS equal to VGS. Source is the reference. So, drain to source voltage is equal to gate to source voltage. This voltage and this voltage are same, because these 2 points are equivalent. Now, what is this drain to source voltage? This DS, that is drain to source, is having the voltage VDS. So, VDS equal to, applying Kirchhoff's law to this part or the loop, rather we have VDD minus ID into RD, that is equal to VDS, and mind it, this ID is DC ID. We are having the DC equivalent circuit. So, we are having the DC current. So, we are having the drain to source voltage as VDD minus ID into RD. So, if this is drain to source voltage, that is also equal to the gate to source voltage. So, VGS is equal to VDD minus ID RD. We can also write then VGS is equal to VDD minus ID RD. So, this expression is one equation which will be giving us a straight line. This is the equation of a straight line only. Now, this straight line will be obtained, or we can draw the straight line provided we know only 2 points. The 2 points are required to draw a straight line. What are the 2 points? The extreme points of the voltage and the current. we are having the axes which are VGS and ID. These are the axes of our interest, because we know that with change of VGS we are changing the drain current. Now, when we have ID equal to 0, we get VGS equal to VDD. That is one extreme point we get when we have ID equal to 0, that is on the x axis, and when VGS equal to 0, we get a point on the y axis or the ID axis. This is the extreme point or the maximum drain current point, which is nothing but VDD by ID, VDD by RD. So, VDD by RD is one extreme point and the other extreme point is VDD. Combining these two, we get a straight line. So, this is the straight line. So, we get from this equivalent circuit a straight line, which is like your load line when we are discussing about the transistor BJT amplifier. Now, our aim is to locate the operating point Q. So, how can we find the Q point? We will be finding the Q point by drawing the transfer characteristic and fixing the ID VGS line on it. So, now in order to draw the transfer characteristic for this enhancement type MOSFET, we know the current relationship, which is ID equal to K into VGS minus VT whole square. Of course, this is in the saturation region, because we are employing the MOSFET under saturation only for amplifier. So, now we have to fit the curve, which is the transfer characteristic, with the help of this equation. Now, mind it, this is not a straight line, it is a nonlinear equation, it is a square term is there. So, it is not enough to get only 2 points, just like as we have drawn for the straight line. We need to have more points in order to fit a curve. For that, one point will help us, which is the threshold voltage. So, gate to source voltage, when it is equal to threshold voltage, the current is 0. That means, on the same axis as we have drawn right now between ID and VGS, we will be taking the same axis ID and VGS. ID is in milliampere, VGS is equal to in volt. Start with the threshold voltage, that is the voltage between gate to source till when current is 0, drain current is 0. So, this is the point, say. One point is on this VGS axis, which is the threshold voltage. Now, another point can be obtained from the specification of the MOSFET given in the data sheet, because generally what is given in the data sheet, they give ID on and VGS on values. That means, these are the measured values for the drain current and the gate to source voltage when the MOSFET is in on condition or in the saturation region. Now, if we know these two values, immediately what you can find out is the constant K, that is the fabrication constant K, because if we look into this expression, K is equal to ID by VGS minus VT whole square. VT is known, it is given in the specification. Now, we are given a pair ID and VGS for on condition of the MOSFET. So, if we replace these values here in this equation, then we get the value of K, which is a constant. So, once we know the constant, for any other value of gate to source voltage, we can find out the drain current. So, let us do that. Let us find out any other value. For any other value, say VGS1, we are finding out the drain current, which is ID1. So, we are getting another point here, and again take a VGS for a current in the higher region, that is, say a higher value of ID2 is given for VGS2, that is another point. So, we have 4 points right now. Joining these 4 points, we get a curve which is the transfer characteristic for this enhancement type MOSFET device. So, now what will we do with this transfer characteristic? We will be plotting the transfer characteristic and the network characteristic given by this straight line ID versus VGS on the same axis. On the same axis of ID and VGS we will be drawing. So, here what we are doing here is that we are drawing this transfer characteristic. This is the transfer characteristic, and this line, straight line, is the straight line for the circuit, that is it is describing the network or the circuit, and this straight line is drawn by just connecting the two extreme points which are given by the VDD by RD value ID maximum, and this is VDD. So, now we have two things on the same axis, same set of axis. We are having the transfer characteristic, as well we are having the straight line. Both are intersecting at a point which is the Q point. So, the intersecting point between the transfer characteristic and the network straight line will be giving us the Q point. So, we know the DC value of the gate to source voltage and the drain current from this Q point. So, this Q point selection must be properly done, so that during amplification we are having the saturation condition maintained for the amplifier. This is one biasing scheme. Another biasing scheme which is used for this enhancement type of MOSFET is the voltage divider biasing scheme. So, this also is looking familiar to us, because earlier we have discussed about the voltage divider biasing scheme while discussing the BJT amplifier. So, here there are two resistances given by R1 and R2, and there is a drain resistance RD and a source resistance RS. This is the ground, and VDD is the biasing voltage. Now, let us denote this drain current by ID, drain to source current, and here also as Ig is equal to 0, gate current is 0 for the MOSFET. Then what happens? We can apply the voltage division principle here. What is the voltage across this R2 that we can immediately write down. That is, voltage across this R2 is nothing but VGS. So, VGS equal to VDD into R2 by R1 plus R2. This voltage is available across this gate to source, not gate to source, gate and ground. So, VG is equal to VDD into R2 by R1 plus R2. Now, if we know this VG, then we can apply KVL, Kirchhoff's voltage law, in the lower loop, this loop. If we now see into the lower loop, we have a voltage VG given by this one, and this gate current is 0. What is this current? This is nothing but ID. Drain current, source current same. The drain current will be only flowing and entering the drain to source voltage source between drain and source. So, the same current ID and IS. So, now if we are writing this Kirchhoff's voltage law in this loop, it will be what? VG minus VGS minus ID into RS equal to 0. So, that is what is written here, VG minus VGS minus VRS means the voltage across the resistance RS. So, that is equal to 0 using Kirchhoff's voltage law. Or we can simplify it further by writing that VGS equal to VG minus VRS, or VGS equal to VG minus ID into RS. This drop across this RS is nothing but ID into RS. Again, if we apply Kirchhoff's voltage law in this loop, upper loop, what will it be in this part? If we are not in this loop, if we can apply this here in the outer loop, VDD minus IDRD, we go this way, not this loop. If we go this way, VDD minus IDRD minus VDS minus VRS equal to 0. So, that is what VDD minus IDRD minus VDS minus IDRS equal to 0, because the voltage across this resistance RS is nothing but IDRS and the voltage across this RD is nothing but IDRD. ID is common because ID is the source current flowing through this RS also. So, we get an equation given by VDS equal to VDD minus ID into RD plus RS. So, this equation is the key equation governing the drain to source voltage. So, once you know the DC drain current, we can find out the DC drain to source voltage. Now, let us take one example for the fixed bias DC biasing scheme, fixed bias scheme which we have discussed just now. It is having enhancement type N channel Mosfet. This is N channel as is symbolized by the this is the symbol for this N channel. So, we are taking this only, and we are having a resistance 10 meg ohm, and the voltage 12 volt is connected through a resistance 2 kilo ohm to the drain. The capacitances are there to block the DC. 1 microfarad capacitance is here, another is here at the output, which is say 1 microfarad. Now, this voltage at this output is say V naught. So, this is our N channel enhancement type Mosfet device. Now, for this circuit, it is given that ID on equal to 6 milliampere and VGS on equal to 8 volt. Also given that VGS threshold equal to 3 volt. You are to determine, find out the operating point, that is you have to find out the DC drain current and the drain to source voltage for the Q point. So, now if we want to solve this problem, so here no, it is not GSQ. That is the Q point, whatever we have seen here, this Q point is actually denoting this two. One is the drain current and the other is the gate to source voltage. So, that has to be found out in this problem. So, we will be finding out basically the transfer characteristic and the straight line, and when they will be intersecting, that point is the operating point. So, operating point will be giving you the voltage and current values under DC. So, now for plotting the transfer characteristic, we need to know at least 4 points that we will be trying for plotting the transfer characteristic. How many points are required? At least we require 4 points, because it is not a straight line, we cannot draw it with the help of 2 points. So, what are the 4 points? 1 point is immediately known from the threshold voltage. So, 1 point is VGS threshold, that is given to us as 3 volt. So, that is known. Second point can be found out from the data given as ID on and VGS on, which are 6 milliampere and 8 volt, because we have this expression for the current given as ID equal to K into VGS minus V threshold square. ID on given to us is 6 milliampere, for corresponding VGS on 8 volt, So, we know what is K. K is ID by VGS minus VT square. So, putting the values here, ID on is 6 milliampere given to us, VGS on is 8 volt, threshold voltage is 3. So, if we compute this 6 milliampere by 25, we get a value 0.24 into 10 to the power minus 3 ampere per volt square. Basically, it is 0.24 milliampere by volt square. In ampere per volt square, if we write, it will be the value of K. Now, once we know K, now it is easy for us to find out the other points, because now we can give a value of VGS and find out the corresponding value of ID, and that we are going to do. But as we have a threshold voltage given by 3 volt, and we know for VGS is equal to 8 volt. So, in between we will be finding another point between 3 volt and 8 volt. Let us find a point, for example 6 volt. So, for third point we will be finding for VGS equal to say 6 volt, that is taken between, as it is between threshold voltage and other point is given by 8 volt. So, we take in between point, set 6 volt. This you can take 5 volt also, but let us take a midpoint around. For what will, for 6 volt VGS, what will be this value of ID? K into 6 minus threshold is 3 square. So, K is 0.24 into 10 to the power minus 3 square 9. This voltage, this value comes to 2.16 milliampere. 3 points we have known. Another point let us take for a higher value of ID. Let us take VGS is equal to 10 volt. For VGS is equal to 10 volt, ID will be equal to 0.24, K is 0.24 into 10 to the power minus 3 into 10 minus 3 square. If you calculate this value, you will be getting the value to be equal to 11.76 milliampere. So, now we can comfortably draw the transfer characteristic, because we know 4 points. This is VGS, this is ID, milliampere, volt. Of course, you have to draw to scale. Let us mark those points 1, 2, 3, 4, 5, 6. Let us draw the scale. Let us take 1, 2 like this, because it will not be over beyond this. So, it is 4, 5, 6, 7, 8, 9, 10, 11, 12 like that. Similarly, 1, 2, 3, 4, 5, 6, 7, 8 like that, 11, 12. So, one point is 3, this point, the other point is given by 8 and 6. 8 and 6, here, this another point. Third point we have taken 6 and 2.16. 6, 2.16 will be somewhere here. Now, if you draw to scale, that will be the correct values, but here I am just drawing only with estimation 6, and the other is last point is 10 and 11.76. 10 is here, 11.76 is somewhere here, say. So, now joining these 4 points, we get the transfer characteristic. Now, the other one, the straight line, which is VGS equal to VDD minus for a bias circuit IDRD. So, ID is equal to 0 means VGS is equal to 12 volt, and VDD is equal VGS is equal to 0 means ID equal to VDD by RD, and that is equal to 12 by 2, RD is equal to 2 kilo ohm. So, we get 6 milliampere. So, we can draw the straight line, one is at 6 milliampere here and the other is at 12 volt. So, joining these two, we get a straight line. This is for the bias circuit. So, now the point where it is intersecting, this is for the bias circuit, this is the transfer characteristic. So, now the point where these two are intersecting, this point is the Q point, and if you draw to scale, this point will be given by the voltage and the current at this point. This is your VGSQ, this is your IDQ, which will be given by 6.4 volt and 2.75 milliampere. So, we get the Q point as 6.4 volt and 2.75 milliampere. So, this is the way how to solve the problem. So, we have to draw the transfer characteristic as well as the bias circuit straight line, then the intersecting point between them will be giving you the Q point. So, in the discussion today, we have seen how the Mosfet is used as an amplifier, that is to amplify a weak signal, how we use the Mosfet in the saturation region, and for properly selecting the operating point, we need to first use a proper biasing scheme, and for that we have seen the two biasing methods. One is the feedback biasing scheme and the other is the voltage divider biasing scheme. So, once we select the operating point properly, then we can now proceed for amplification of the weak signal, and so we will be analyzing the Mosfet amplifier next by using the small signal model of the Mosfet. So, next we will be discussing about the small signal model of the Mosfet and use it for finding out the parameters of the amplifier.